Okay, let's unpack this. Imagine printing a custom plastic part, um, like a drone frame or a bracket, and it actually handles shearing forces like solid metal.
Right, instead of just snapping like a bridge built out of dry spaghetti.
Exactly. Building a bridge out of dry spaghetti is basically standard 3D printing. But today's deep dive is on a 2026 paper from Fracture and Structural Integrity by Labov and their team, and they completely flip that. The secret for you to discover today is the microscopic angle of carbon fibers.
Yeah, manufacturers are moving way past just melting standard plastic filaments. This paper investigates a hybrid method. So they feed a continuous strand of solid carbon fiber straight into a plastic matrix, like right as it prints.
And they aren't using just any plastic, right? They use materials that already have microscopic shock fibers mixed in.
Yeah, precisely. Stuff like ABS or PA12 and PTG, which, have a bit more natural flex to them.
But wait, how do you get a dry, continuous carbon fiber to actually bond with a melting plastic mid-print? I mean, wouldn't it just pull right out the second you put weight on it?
You definitely think so, but the process is called in situ impregnation. The 3D printer nozzle is actually coating that continuous fiber bundle with the molten thermoplastic at the exact microsecond it's laid down.
Oh, wow. So it weaves a load-bearing framework directly inside the part. That sounds basically like microscopic rebar being poured into concrete.
The rebar analogy is actually perfect for understanding the internal reinforcement, but having the rebar isn't even the real breakthrough here. It's testing exactly which direction that rebar needs to face to maximize the part's strength.
Really? How much difference does the direction actually make? Like if I'm printing a part, does angling the fiber by a few degrees change the structural integrity that drastically?
Oh, it completely transforms it. The researchers tested laying these continuous fibers at angles of 0, 30, 45, and 60 degrees relative to the direction the material gets pulled.
Okay, so what happens at 0 degrees?
So at 0 degrees, where the fiber is perfectly aligned with the pulling force, the stiffness skyrocketed to over 40 to 60 gigapascals.
Wait, isn't that approaching the stiffness of aluminum?
It is. But there is a catch. As soon as they increased that angle, the raw pulling strength just plummeted.
Well, if 0 degrees is by far the strongest by that massive of a margin, why on earth would anyone print layers at 30 or 60 degrees? That sounds like designing the part to be weaker on purpose.
What's fascinating here is that real-world objects don't exist in a vacuum. If you build a bridge or an airplane wing, the force isn't just pulling perfectly straight down.
Right, you have wind, torsion, and shear forces hitting it from multiple directions.
Exactly. If you only print at 0 degrees, your part is incredibly strong in one direction, but highly vulnerable to splitting in others.
Oh, I get it. A side impact would just crack it right down the middle, kind of like chopping a log along the grain.
Precisely. The researchers found that off-axis layers, those 30 or 60-degree prints, prevent the plastic from failing under shear stress. The angled layers essentially create a maze for the stress forces.
So instead of a crack shooting straight through the plastic, it hits an angled fiber and gets deflected.
Right. In engineering terms, it creates a mixed mode 1 and mode 2 failure, which basically stops the part from just abruptly shattering.
Okay, so we need 0 degrees for pure pulling strength, but we need those off-axis angles, almost like plywood, to stop cracks from spreading. How do they combine them without compromising the overall strength?
They designed what the paper calls a quasi-laminate architecture. They tested a specific combination, layering fibers at 30 degrees, then 0 degrees, then negative 30 degrees.
Putting that 0-degree load-bearing fiber right in the dead center.
Yeah, sandwiching it between the angled fibers, you get a central spine for raw strength wrapped in a crack-resistant skin.
Here's where it gets really interesting, though. How did that specific sandwich perform compared to just mixing up the angles randomly?
It drastically outperformed the others. When they tested a layup of 30, negative 30, and 30, which skips that 0-degree spine entirely, it lost 64% of its overall strength.
Wow, 64%. So you absolutely need that central load path.
You do. And the type of plastic acting as the glue around that spine plays a huge role in absorbing the remaining impact. Like ABS proved to be highly brittle when the angles changed.
But the PTG matrix still acts as the ultimate shock absorber, right?
Exactly. When paired with that 30-0, negative 30 architecture, PTG achieved the highest ultimate strain overall. It actually stretched by nearly 3% before finally giving out.
That is a massive amount of energy absorption for a structural component. So to build a true supermaterial, you need all three elements working perfectly together.
Right, you need that continuous 0-degree load path for raw, unyielding strength.
Balanced with those angled layers cross-hatched around it for damage tolerance and, a flexible polymer matrix holding it all together.
If we connect this to the bigger picture, it leaves you with a really fascinating thought. If additive manufacturing can now weave custom, multi-directional strength layer by layer like this, layer by layer?
Are we on the verge of 3D printing synthetic structures that actually mimic the flawless, highly optimized fiber networks of human bone or muscle?
I think we just might be. It's definitely something for you to think about the next time you hold a printed part.